Welcome to Labster. Here you will learn about radioactive decay. Look up to the sky. We are in the middle of a meteor shower. Beautiful, isn't it? This simulation uses voiceover. Using the lab pad is an important way. Perfect. Then let's get started with your first mission. Wow, a meteor has fallen to Earth. As physicists, it's our job to investigate. Let's find out what's going on. Pick up the Geiger counter from the table. This is a Geiger counter. We use it to detect radiation. The faster the clicking sound, the more radiation we are detecting. There is also a visual readout on the screen. Take a step closer to the meteorite. Click the marked area to approach the crash site. There is always some background radiation on Earth. This comes from rocks in the ground, gas in the air, and even from the sun. Bananas are radioactive too. Take another step closer. Oh yes, the activity on the Geiger counter has increased. The rock certainly seems to be radioactive. Approach again to make sure. Get a little bit closer. It's active, all right. Let's step back to be safe and bring a sample back to the lab for testing. I think I know just the person to help. Ray, are you ready to return to the lab? Great. Then let's head back. Hold tight. Phew. Okay, we are back in the lab. Time to introduce you to Madame Curie.
Hello, my name is Marie Curie. I lived between 1867 to 1934. My work on radioactivity in the past will help you learn about it today. Maybe we can even work out what's in that rock. Radiation is extremely useful, but it can be harmful to humans, so let's be safe and wear some protection.
Pick up a lab coat to wear it. Click on the workbench.
I know a lot about radioactivity. I discovered radium and polonium, which I named after my home country Poland, investigated radioactive phenomena, and used it for medical X-rays to treat injured people in the First World War. It is far too dangerous to handle the sample yourself, so Dr. One will do that for you. But just to be safe, let's protect our hands with some gloves.
Find a glove box and click on it.
To this day I am the only person to have been awarded the prestigious Nobel Prize in two separate scientific fields, physics and chemistry. I'm a pretty big deal. Just a few more safety measures. We're almost ready. There is a dosimeter on the workbench beside you.
Pick up the dosimeter to attach it to your lab coat. The dosimeter will monitor your exposure to...
Perfect. Now we are safe to enter the lab.
Click the doors to enter the lab. Okay, if we are to work out what's in our space rock, we need to understand a few things about the atom. Let's get started. Atoms are made of three key parts: neutrons and protons that bind together to form the nucleus, and electrons that orbit outside the nucleus. We call a nucleus with a specific number of protons and neutrons a nuclide. Only nuclides with a special balance of protons and neutrons are stable. If this delicate balance is disturbed, nuclides become unstable and likely to break down. We can investigate this idea of stability by building our own nuclides. Go to the hollow floor. Take 2 protons and 2 neutrons from the side and place them in the center of the hollow floor, then press play to see what happens. Great job! This is a helium nucleus. It is extremely unlikely to break apart on its own. This makes it very stable. Add another neutron to our nucleus and hit the play button. Nice one. This nuclide was unstable and unable to hold itself together, releasing radiation. When a nuclide is so unstable that it breaks apart, it releases matter and energy. This process is called radioactive decay. It's time to check what we have learned so far. What is a nuclide? Well done. A nuclide is the name we give to a nucleus containing a specific number of protons and neutrons. Which description best applies to a stable nuclide? That's it. Remember that the more stable a nuclide is, the harder it is to break down. We use numbers to help keep track of radioactive decay events. There are two important ones to remember: the mass number, A, and the atomic number, C. The mass number gives us an idea of how much each nuclide weighs, and is simply the sum of the number of protons and neutrons in each nuclide. C, the atomic number, tells us how many protons we have in a nuclide. It also defines which element we are dealing with, as each element has a unique atomic number. Neutrons and protons have a mass number of 1. They are very close in weight. Electrons, however, have a mass much less than either protons or neutrons. In fact, they are so light that we give them a mass number of 0. The atomic number is a little different. Protons have an atomic number of 1, neutrons have an atomic number of 0, and electrons have an atomic number of -1. Weird, right? We combine our understanding of A and C into decay equations to better understand what is happening inside a nuclide during radioactive decay. Take a good look. After you're done, it's time for another quiz. What is the mass number of an electron? Remember, you can check the theory page if you get stuck. Guess again. Remember, you can check. Exactly, the electron has much lower mass than that of a neutron or a proton, so low that we give it a mass number of 0. What is the atomic number of a proton? Yep, that's it. A proton has an atomic number of 1. What is the mass number of a proton plus the mass number of a neutron? Good job, a neutron has a mass number of 1 and so does a proton. Add them together and we get a mass number of 2. There are 3 key ways in which unstable nuclides decay: alpha, beta and gamma. We use some special notation to keep track of these radioactive decay events. On the left of the arrow, before the decay event, we have our parent nuclide. To the right of the arrow, after the event, we have our daughter nuclide and any radiation. Recall the numbers A and Z? They must be balanced on either side of the arrow. The A before the decay event must equal the sum of the A's after it. The same is true for Z. Select the alpha decay button on the floating screen and press the play button on the hollow floor. The unstable parent nuclide undergoes a radioactive decay event, ejecting an alpha particle. It looks exactly like the helium nucleus we built before, and contains 2 protons and 2 neutrons. This means it has an atomic number of 2 and a mass number of 4. Balance the equation on the display. Try again. Remember, the daughter nuclide is losing the mass ejected by alpha decay, so its A and Z numbers will be less than the parent nuclide. You can view the theory page if you need a reminder. Well done. Great work. Now let's take a look at the second type of decay, beta. Select the beta decay button on the floating screen and press the play button on the hollow floor. This time the unstable nuclide ejects a beta particle, which can be thought of as a high-speed electron. The beta particle has an atomic number of -1 and a mass number of 0. Very strange. Balance the equation on the display. Yes, since the beta particle has A equals 0 and Z equals -1, the daughter nuclide must gain Z equals 1 to balance the equation. Almost done. Head back to the hollow floor to watch a gamma decay event. Select the gamma decay button on the floating screen and press the play button on the hollow floor. Gamma decay is a bit different from the other types. It occurs when the nuclide has too much energy and needs to relax. It does this by emitting a high-energy photon called a gamma ray. The gamma ray has an atomic number of 0 and a mass number of 0. Balance the equation on the display. Good job! Well done! Do you remember everything you've learned so far? Does the mass number change in a gamma decay event? Good work! In gamma decay only a gamma ray is emitted, which has a mass number of 0. Which decay type ejects the most mass? Yes, that's it. Remember that an alpha particle is made of 2 protons and 2 neutrons, each having a mass number of 1. Altogether that's 4, the largest ejection of mass of all the decay types. What is ejected in a beta decay event? Correct, a beta particle is a fast-moving electron. Good job! After a parent nuclide has undergone some sort of radioactive decay event, the daughter nuclide it turns into can also be unstable. The daughter nuclide itself can then undergo a decay event producing a granddaughter nuclide. This process is called a decay series and will continue until the nucleus reaches a state where it is bound together tightly, becoming stable. There is a screen in the middle of the room prepared for your next task. Go to the workbench by the board. In this example of a decay series, a neptunium nuclide decays by a series of alpha and beta events, eventually ending up as an actinium nuclide. Follow the arrows on the display board to track the decay events. What happens to nuclides after they decay? That's it. Daughter nuclides may or may not be unstable, depending on their balance of protons and neutrons. How long do decay series go on for? Well done! Decay series will continue until they produce a stable daughter nuclide. Generally speaking, daughter nuclides are lighter and less energetic than their parent nuclides. Great work! As radioactive decay occurs, material and energy are ejected from nuclides and they become lighter and less energetic. A neptunium nuclide is about to undergo alpha decay. Select the correct daughter nuclide from the tiles on the rack, and drop it into the right slot on the display board. Click the view theory if you need help. Well done, that's it. After neptunium-237 decays by alpha decay, it becomes protactinium-233. The protactinium nuclide is itself about to undergo beta decay. Select the correct daughter nuclide. Remember, you can click the view theory if you need help. No, try again. Remember, a beta particle has A equals 0 and C equals -1. We must subtract these A and Z numbers from the parent nuclide to produce the daughter nuclide. View the theory page if you are stuck. Yeah, that's it. After protactinium-233 decays by beta decay, it becomes uranium-233. Now the uranium nuclide will undergo alpha decay. Select the next daughter nuclide. Well done. After uranium-233 decays by alpha decay, it becomes thorium-229. Now the radium nuclide will undergo beta decay. Select the next daughter nuclide. Well done. After thorium-229 decays by alpha decay, it becomes radium-225, which then decays again via beta to become actinium-225. You have completed the decay series. Great, that's it. You have completed a 6-step decay series. Well done. We're really getting somewhere now. There is just one more thing we need to understand before we can analyze our meteorite: half-life. The half-life of an active nuclide is the length of time required for half the active nuclides in a sample to decay. This can be a tricky concept to get your head around. We can imagine our nuclides as coins. The coins are marked on one side, in this case they are yellow. Marked coins represent active nuclides while unmarked coins represent decayed nuclides. After some length of time, a half-life, we can flip all the coins leaving half left marked and half unmarked. This process can be repeated, leaving only half left each time. There are 16 coins on the hollow table. They are marked with the Labster logo on one side. Assuming marked coins represent active nuclides, can you guess how many will remain marked side up after one half-life? Great, that's right. After the first half-life, 8 marked coins remain. Can you find this point on the graph? Good job. After the same length of time, another half-life, we flip the remaining marked coins again, leaving only half left. Now only 25% of our original coins are still showing the Labster logo. Take another look at the hollow table. How many? Aha, that's it. After 2 half-lives, only 4 marked coins remain. Can you find the corresponding point on the graph? No, sorry. Remember, 4 coins remain logo side up after the second half-life. That's it. After the third half-life, only 2 marked coins remain. Find the last corresponding point on the graph. Great, I think you're getting it. Time for a quiz to check your knowledge. What is meant by the term half-life? Exactly. After one half-life, only half of the initial radioactive nuclides remain. After 2 half-lives, how many of our original nuclides do we have left? Well done. After one half-life, only half of the initial radioactive nuclides remain. And after another half-life, only half of those nuclides are left. Imagine cutting a cake in half, and then half again, only a quarter remains. Which answer best describes half-life? Yes, that's it. The half-life of a nuclide is always the same length of time. Alright, that's it. Let's take a look at our meteorite sample, and try to calculate its half-life. I have produced an activity graph for you. Take a look. Okay, this is it, the last step. Take a look at the graph. Can you work out the half-life of our sample? That's right. Our sample seems to have a half-life of 15 days. I wonder if Madame Curie can help us identify it? Let's go and talk to her again. Click on the doors and exit the lab.
Our sample has a half-life of 15 days? Radium-225 has a half-life almost 15 days. It must contain radium. Great work, and thank you for all your help. I'm proud to say you have become an excellent radiation scientist.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.